through some stuff for the summer school, and now up for something totally different, but still GPs though. So I'm going to talk about constraining Gaussian processes by something, and you'll see what the constraints are. But at this point, I just want to say that this is mostly based on a recent paper which I published at AI Stats last spring, and also building on some previous work, like earlier work. So the paper at AI Stats was with Mann and Koch, and the earlier work is basically a paper with Nicholas and James, and an even earlier one with Simo from years back. But let's dive into the actual content. So we have 1 hour, so I'm sort of first going through a bit of sort of background, and then diving into the actual beef then later on the talk. And it might go a bit technical at some point, but don't worry, we will get back to the nice figures and examples in the end. So don't fall asleep in between. So first, I'm going to formulate the problem, what sort of constraints we are going to look at. Then there's quite a lot of details regarding the model and actually how to set up like a low rank construction for the kernel of interest. And then well, when the model is set up and so on, the prior is totally clear, then it's nice to apply this to like more general problems like classification and so on. So then there's some examples of that, a couple of examples, and then also a sort of a bit of an separate thing. Basically, the motivating problem for actually this, like looking into these things, came from something very applied, how to do localization and mapping. So I have an example where actually this is used then in that framework. And then some concluding remarks. Great. So let's get started. This tries to visualize the idea. So consider you have a domain of interest. Your data is inside some typically low-dimensional domain. In this case, it's a star-shaped thing. And you have some boundary conditions along this boundary. Say you know that the latent process has a certain value on the boundary, or its derivative has certain values on the boundary, or something else. But typically, it might be that you know that the thing goes to 0, like smoothly on the boundary, or then that the derivative goes to something, or so on. And then you have some data inside your area of interest. And then, for example, here it's just a regression problem. So I have some observations of something, and I know that the latent functions are smooth and differentiable inside the domain, but they also sort of go smoothly to 0. And then I want to do prediction or like explorative analysis in that domain. So this is sort of the problem. How to set up a GP prior with these properties. And preferably also do that in a way that can be scalable in terms of like number of observations you have, and also then easily like applicable in various kind of problems. So well, you at this point you all know about GPs. So you know that they are like a powerful framework for doing various things. But then this is actually a practical thing that we encountered in the SLAM thing that I'm going to show in the end. So how to actually like impose these sort of boundary conditions in like a generally shaped domain, which you sort of know a priori what the domain is like, but so how to actually do this in a smart way. And of course, like these sort of boundaries are quite typical in practical applications. You might have some knowledge from physics that there are some sort of constraining boundaries, or then in say brain image analysis, you know that something is constrained to the surface of the brain in a certain way, or then in robotics, you might sort of have geometrical constraints, or then in just general ML tasks, there might be constraints. There's a question.
Yes. So to understand completely correctly, you are meaning some boundary conditions on like x's or on values like y's?
On values y's, so basically at some continuous values of x's, so like the inputs which are along the boundary, you know something about your outputs. You might not know that it's exactly 0. Or you might know that in your classification problem you're absolutely uncertain in this region. There's no way you're gonna assign that region to any class, for example. Or things like this, depending on the problem. Good. So why is this non-trivial? First of all, how to represent such a prior? That's maybe the first question. Then, of course, there are the usual problems. Then, how to scale this to large data sets and do that in a very efficient manner, which actually was the motivating thing from the positioning application, the SLAM application. And then also the usual thing with GPs, there's like the first problem is usually like you might have a lot of data, or then the next problem is that what if the likelihood is non-Gaussian? Then you need to resort to some sort of approximations. So these are sort of the questions. And now before going to how to represent the prior, I'm going to go through some earlier work which we then leverage in setting up the prior. And this earlier work is actually something that like a project or a method which I like a lot. It's one of my personal favorites of my publications. And usually when you're very proud of something and you really think that this is very good, then typically the reviewers aren't as happy about things. So this paper has actually been on archive for like 5-6 years. And now sort of, because it was crashed when we submitted the first time, and then we just left it in our archive. We were so depressed about it. And then some year ago, like a bit more than 1 year ago, we resubmitted it then. And now actually, some weeks ago, it was finally published. So sometimes it can take a while for papers to be published, but it's actually used quite a lot. It has gotten a lot of citations. So we are not the only people who are very happy about this method. So let's start with looking at the normal Gaussian process regression problem of this form. So you have your prior and your Gaussian likelihood. And then like the usual problem here is that if you have a lot of data, if your y is big, then you need to invert a big matrix, and then you have problems. And of course, so if you look at these things here, you can write down the posterior in closed form. So then you have these like matrix inverses appearing here. And of course, there's like a multitude of methods how to deal with this problem. And I think there's not just one good method. It's typically like depending on the application you have, or the type of prior you have, or the dimensionality of inputs, or how the inputs are ordered, are they on a grid, so on, which is sort of the way to deal with these problems. But then let's think a bit more of what is actually happening here. So, well, you have been talking about covariance functions most of the week, actually, I guess. So then you can also think of the covariance function actually defining a covariance operator. Call it K here. This is the point where it starts to get a bit technical. And for a stationary covariance function, we talked about this yesterday. For those of you who were here, might recall that you can represent a stationary covariance function also in terms of its spectral density function. So basically the Fourier transform of that. And of course, there's like a connection between the covariance function, the covariance operator, and the spectral density function. So this is just sort of the different sides of the same thing, basically. Okay. And now if you think of what the spectral density, the spectrum of the covariance function is actually representing the eigenvalues of the operator in a formal sense. You can think of it in that way. Then again, if we think of something of like expanding the spectral density function in terms of a series, and then if you look at the series here, you have these omegas, which is the sort of spectral variable here. And then if you go back to your like Maths 101 or something like that, you might recall that this is the Fourier transform of the Laplacian, the Laplace operator, the second derivative in 1D. So then if we plug in that here, we actually have like the pseudo-differential operator as a series of several differential operators here. So let's now approximate this with the so-called Hilbert method. So if you think of the covariance function and an inner product of this form, we can then set up an approximation which is basically like a basis function expansion of f. So you project your f, your function, on a set of basis function phi, which are coefficients fj in front of them. So now if we select the eigenfunctions phi, in this case, the basis functions where we project the f on, of the original covariance function with respect to the inner product we use, we actually get something called a Karhunen-Loewe series, where the coefficients fj here are actually just independent Gaussians. The interesting thing is then when we sort of continue this, so now we have sort of a bunch of some weird basis functions and some coefficients in front of that. So we are sort of getting quite deep down in the swamp here. But let's say that you have some domain, some arbitrary domain omega, where your inputs are. So then if you formulate this as an eigenvalue problem of this form, which is just a very basic eigenvalue problem, and if you somehow manage to solve the problem in the form that you have a parametric representation for your eigenfunctions and your eigenvalues, then you have something to work with actually. So let's say you choose a domain. It might be like in 1D, it might just be a piece of the real line with some boundary conditions in this case in order to make it solvable. 0, you make the functions go to 0 in like your piece of the real line. So then, for example, in this case, you recover just sinusoids in this. And then, of course, if your domain is a cube, you have like a product of sinusoids with respect to the different dimensions. Okay, so if you can solve this, then you can actually get something to work with. So now we're sort of plugging things together. So you had that covariance operator, which we expanded as a series. And the covariance operator is kind of operating in the same way as your covariance function, where you have your prior knowledge. And now we substitute that operator with the former kernel that we had on the previous slide. And we get it's still a series. And then by regrouping, we actually have a series then of like the covariance function is basically an infinite series of some eigenvalues from the Laplace operator, and then the eigenfunctions here. And now if you think of that you evaluate the spectral density of corresponding to the original covariance function, and then you plug in this was on the first slide, you plug in this here, then you can actually come up with a quite simple approximation for your covariance function. Okay, so now if you forget everything that I presented before and just stare at this thing, what does it say? It says that the covariance function, which needs to be stationary in this case, can be approximated by an infinite sum, or here it's approximated, so it's like a finite sum in this case, of the product of some basis functions, which are basis functions of the negative Laplacian, and the spectral density of the covariance function. So this is basically an eigen decomposition of the covariance function, but instead of needing to solve the actual eigenfunctions for that operator, basically, this tells you that you can replace those with the eigenfunctions corresponding to the Laplace operator. Okay, might sound strange, but this is actually very, very nice. This is an extremely nice result in practice, because now you can then, of course, like you can set an approximation. These are then just plotting what the covariance function would look with this approximation for the Mattern class of covariance functions. There's the exponential, the Mattern 3-2, and then the exponentially quadratic in the end. So actually, just with a very small number of basis functions, you get a very good approximation for your prior. And of course, like now, what is required if you look back on this? So basically, you need the spectral density function corresponding to your covariance function. That is easy. Just Fourier transforming the covariance function, or then, well, looking it up in a book or something. And then you need your basis functions for the Laplace operator in some domain. And that can be the tricky part. So the eigenfunctions of the Laplace operator, they are solvable in closed form for many sort of simple domains, like spheres, cubes, so on. And then, for example, for a sphere, there are sort of bunch of like quite complicated like Bessel functions and so on, but still like solvable in like closed form expressions. And here, for example, it's just random draws from a GP with a Mattern 3-2, 1-2, 3-2, and squared exponential with some fixed hyperparameters. So then you can come up with random draws easily. Why is this then actually nice? The nice thing is here that if we now look at the end of the simple regression task, so now actually what this says that you can project your GP onto a finite basis which correspond to the basis functions of your prior, which is actually quite nice. So, and then of course, like if you think of what an eigendecomposition does, it actually gives you the inverse sort of free of charge, because you have, instead of having to invert the big matrix, you actually have the eigendecomposition, which is a matrix times a diagonal matrix times a matrix, and then you can just sort of invert the diagonal matrix in between, which is sort of extremely cheap, of course. But there's more. The thing is that the basis functions themselves, according to this, they do not depend on the kernel. So the only requirement is that the kernel must be stationary. And this also means that the hyperparameters of your kernel do not enter the basis functions, which is actually really confusing. And that means that, for example, when you do GP regression and you want to optimize your hyperparameters, there's no need to recompute the basis functions on every step. So there's one operation here when you solve these things which takes nm squared, like ONM squared operations, where n is the number of data points and m is the number of basis functions you choose, like inducing features you could think of. But this is only need to do once. So basically you only need to calculate that thing once. It's sort of setup cost. And then when you run this thing for actually doing hyperparameter optimization or so on, you only need to invert, or basically not invert even, so like your OM cubed. So you're cubed in your number of features you have. And this actually makes this method extremely fast. And it's sort of hard to underline how fast this is. So after the brewer tour yesterday, I went back to the hotel, and I was thinking that I should probably update my slides still. So I decided to make you an demonstration of how fast this is. So let's consider a data set. This is like a standard sort of benchmarking problem. So the data set contains all flights in the US for year 2008. I think this was originally in one of James Hensman's papers. Alan is doing this, so yeah. And then the typical inputs that are being used are, there are 8 inputs: the age of the aircraft, the route distance, airtime, scheduled departure time, arrival time, day of the week, day of the month, and the month. So there's 8 inputs. And the target is to predict how much the plane is delayed at landing. Okay, so, but still, let's just think that we have a big GP regression problem. And here, it's actually been quite typical to look at this sort of as an additional, like additive GP model, where sort of the kernel is set up as a sum of squared exponentials over the different dimensions. So this is basically the model. And now let's see if my online demo works. So recall that the paper is from 2003, like the method is from 2003 originally. So the code is in MATLAB, and I had to dig it up for you to. So I start by just loading some data. So it's like the 6 million data points. Let's see, it should be. So if you look at size of X, there are like 5.9 million data points with 8-dimensional inputs. Then let's set up a model where we have sum of these various squared exponentials across different dimensions. It's this horrible MATLAB code doing that. Okay, so that's sort of no time spent. So now is the heavy part. We need to calculate that inner product of the phi matrices. And this will take a while, because now you have like 6 million times 8 times, I think I used 40 features. Yeah, m is 40 here, which should be quite enough. So this is the heavy part. And my experience with demos is that usually my computer crashes at this point or so. But let's see. "26 seconds spent on that." Okay, that was the heavy part. Now let's optimize the 17 hyperparameters that we have. So there's 2 per kernel, and then the noise scale. Let's do that. And now look closely, because this is not taking long. Done. That was fast. And then we can do prediction. Let's predict per component. So I say this really, really fast, and I really mean it. So basically, yeah, this tells that there are the air time, travel distance, the time of the day when it departures, and the scheduled arrival time are the ones most affecting the delay. Kind of makes sense. Okay, so this was the background of sort of how, like, quite a formal derivation of how to actually set up a way of projecting or like approximating stationary covariance functions in terms of basis functions from the Laplace operator. Question?
So how is this different to, Fourier features or, kitchen sinks, or because, in that original paper, Rahimi, you already have a representation of your kernel as inner products of basis functions,
So
which are complex exponential.
Yeah, so then, but for example, if you think of the random Fourier features paper, which just was referenced in one of the talks earlier, so there basically you have a kind of like a Monte Carlo approximation for, while this you could see this as like a quadrature approximation for the same integral. So instead of solving the integral by like the Fourier transform integral by Monte Carlo, this is like a kind of like a deterministic approach, like a quadrature approach for that. So there's actually a lot of discussion about this in both the paper by me and Nicholas and James, and then in the original paper by me and Simo. So there's like a quite a long discussion. So actually you can see all these methods as just different ways of solving that one integral, basically. Yeah. So the cost here, of course, is that sort of you need to have your basis function solved in closed form. And also, if you have high-dimensional inputs, here the model was additive. But if it would not be additive, it would just be like a product across the dimensions. Then you would need to fill all those dimensions with basis functions. So that would actually be very costly. You would need a lot of basis functions to fill that. If you think of like having a higher dimensional integral, doing quadrature then needs like more quadrature points across all the dimensions. So then it becomes heavy. So in that case, sort of like having like a Monte Carlo approximation would actually be a smart thing to do. Yeah. Okay, so going back to the star, there's a question.
So you're using the eigenfunctions of the negative Laplacian here, and is the reason rather than the eigenfunctions of the kernels, and is the reason for that just that they're more often available in closed form?
They're available in closed form, and it's sort of simpler to actually like set them up, because then they don't. The key thing for speed here is that the basis functions do not depend on the kernel.
Right, but they would obviously.
Yeah, but then actually like in the limit of like having infinite many basis functions, you can actually show that these two converge to the actual representation, which is sort of very interesting. But it kind of makes sense because there's like there's been a lot of like papers on the connection between the matter family of kernels and then like differential operators. Or it's not surprising that it works like this. Yeah. Alan.
So for each step in which you want to change your hyperparameters, you just need to take Fourier transform or find spectral.
You evaluate the spectral density function. Yeah. So going back to this original problem then. So actually like in the method which I discussed just now, you kind of end up with boundary conditions which you might actually not want. So you just need to have some boundary conditions in order to have the basis function solvable in closed form. But we can turn that into our benefit as well. So if we are able to solve the eigenfunctions of the Laplace operator in a domain of any shape with respect to certain boundary conditions, then we can actually directly plug that in to the theory that I just presented to get an approximation for the covariance function in that domain. And if you now look at the issues, how to represent the prior, that would sort of solve that. How to deal with the limitations of large data sets, that would also solve that. Well, it doesn't sort of do anything for the third issue yet, but it would kind of solve the first two. So as a pre-processing step for our star-shaped domain, let's try to solve the features, the harmonic features or the basis functions to project the problem on. And that low rank representation would then also sort of represent the prior and speed up inference. And basically, the computational complexity would be linear in number of data points and then cubic in number of features for hyperparameter learning, which would be very nice. And then we'll later on have a look at sort of how to then plug this into like a variational framework for dealing with the non-Gaussian likelihoods. So okay, let's start looking at the eigenvalue problem again. So here, our negative Laplacian in our domain, which now can, for example, be the star-shaped thing, and with some boundary conditions, which in this example, for example, here is that the values go to 0 along the boundary. And of course, like, it's probably not available in closed form for a star-shaped domain, which is kind of reasonable. But, well, having some domain of some shape, like this squirrel-like thing here, and then combining that with actually the negative Laplacian, so we can do like a finite difference approximation for solving the problem. So basically, you can discretize your domain or like triangulate it or whatever you like. Here, for example, I just discretize it to a grid, approximate the negative Laplacian with like a finite difference approximation in the grid, and then plug that into like a numerical solver for the eigenvalues and eigenvectors for that already discretized problem. And it turns out to work very nicely. So for example, if you think of this domain, which is actually quite challenging with all the sort of like weird shapes, this would be what I get. This would be the first 15 deterministic basis functions for that problem. And it kind of makes sense. There's some very large scale thing first, then some sort of these bumps in different directions and so on. And of course, like in this case, these are now orthonormal. So if I take the inner product with respect to any of these, they sort of cancel out, which is really nice and enables this thing to work. So then now we have the basis functions. We have the eigenvalues. We have the spectral density from our Rothschild prior. So now we have everything that we need basically for setting up an approximation here. And the computational boost is actually quite significant. So here I have some examples of various domains. So here's like the star, which you've seen before. There's a random draw from Matern 1, 2. There's a car, there's a crab, there's a train, there's Japan, there's this piece of art, a mug, cheese, and Japan again with different GP priors and then random draws. And in all of these, the value goes to, like, smoothly goes to 0 on the boundary. And as you see, there can be sort of holes in the domain, and they can even be disconnected, even though in that case you could just like treat them as separate. Okay, so then actually like the part with the non-Gaussian likelihoods is sort of a bit maybe uninteresting, because this is more sort of plug and play in the sense that there's a question.
Excuse me, can we do this without boundary conditions? So this approximation only.
So basically, you need to solve the basis function somehow, and you need to basically, in order to solve the problem, you need to constrain it somehow. Otherwise, it's impossible to get like a closed form representation or a representation for those. So typically, what you would do in like a general case would be that your data is let's think of 1D problem. So your data is, there's like a real line. So your data is here, these points. So then you just choose sort of some boundary, like far enough from the data. Couple of length scales basically away from the data, and then say that, well, let's say that the process goes to 0 here. That's sort of the typical way of dealing with this thing.
And can I maybe say that they should decay at infinity at some rate and solve PDE with this condition and get what I want?
Yeah, so you could also think of not having like a deterministic boundary, but instead having like an input density. So you would assume your inputs to have sort of a Gaussian density where they occur, and then that would sort of give you an approximation which would get worse, like when you go to infinity, but sort of that would be like an alternative way of setting it up. Question?
So now that you have to do when you want to specify the boundary, you said that so the addition now is that you need to do these finite element methods.
Exactly. Yeah.
So how does that step affect the computational complexity?
So that step, the nice thing is again that you only need to do that once for every domain, which actually sort of you have your domain, you solve the eigenfunctions, eigenvalues once, and then you're done with that. So it's only like a one-time cost per domain. In these examples, so these are relatively simple domains, these. So I think the time for doing this in Python or MATLAB or whatever is like 500 milliseconds or something like that, with quite a finite grid. The solvers are actually really good nowadays. Then if your domain is really big and then you have a very tight discretization, then it takes longer. So then it depends on how complicated your domain is and how you set up the sort of discretization. Yeah. Question?
So if I understand correctly, the kernel you get out of this on this domain is not the same as the original kernel you started with.
It's basically, I think I should have, let's see. I might have skipped. Yeah. So your original kernel is actually that you have a like a separate GP problem where you say that, well, the problem follows, say, a squared exponential.
A stationary kernel.
Yeah, some stationary kernel, basically. Subject to the function values obeying a boundary condition. So basically, if you like really simplify, you could think of having like a lot of data along the boundary, like just observations, and you would first solve a GP regression problem.
Okay.
And then use the posterior for that problem as the prior for
So
this.
it's equivalent to what we're doing.
Yeah.
Okay.
Okay, so then, sorry.
So is this, so another way we could get the same kind of GP over that domain would be to start with a kind of a linear PDE and then a Gaussian sort of source function,
Mm?
and then convolve the Laplacian over that source function. And that should also obey the boundary conditions. Is this way of starting with the Gaussian on the output preferable? Or are there cases where those two different approaches do the same thing?
So let's get back. So
you have like a linear differential operator,
yeah.
and then you have some Gaussian input, and then you kind of solve that PDE, and that's going to be a linear.
So yeah, if the operator corresponds to your covariance function, yeah.
Yeah.
Then it should be equivalent, I guess.
So
Yeah.
input latent force. And
Yeah. So it should. Yeah. It should be kind of the same thing, just sort of from a different perspective.
is it possible to show when one kind of input would get the same kind of? Because I guess I understand it's like taking a stationary kernel and then getting the best approximation in terms of basis functions that respect the boundary, a certain class of basis functions that respect
Yeah.
the boundary. There's like the two different ways of starting.
Yeah, I think it should be equivalent when you sort of approach it from both directions, kind of. Yeah, indeed. that's more of like a how like a physicist would probably like look at this. I guess, yeah. So for the non-Gaussian likelihoods, we set up a sort of a like take the variational machinery and put this approximation in there, and then basically use the deterministic features we have as features inside the model, and then basically use free-form optimization for the variational parameters in with the optimizing the elbow. So I have a couple of examples of this. In the AI stats paper, we compare this to different approaches where you could, of course, like have measurements along the boundary, specifying what sort of value you want to have there, like zero noise measurements along the boundary, and then use some like general purpose scheme for the inference then, such as like FITC or VFF, and then of course it's not surprising that a general purpose method where you actually can encode the continuous boundary inside the method actually works better than just using some general purpose approach. So for example here we compare our method to like the baseline is having a full GP with just a whole bunch of zero noise measurements along the boundary, and we compare that then to VFF, variational Fourier features, and FITC with these like pseudo measurements, and turns out that works actually very well, which is kind of not surprising. It's a bit unfair maybe. So then we also look at classification. Question.
Question to the previous graph. So to match the performance in a way between the generic FITC we put in like specific observations to the newly proposed method, I would basically need to add, in this case, like 80 more
Measurements,
right?
Indeed.
In the domains that we're talking about here, in this example where this might be a relevant approach, can you comment on your experience, like how much of a difference does that effectively make, those 80 additional observations?
It like in terms of computational scaling, or
For example, yeah.
so of course, like if you have like we compare to naive approach. So if you have a lot of like new measurements, of course, like if you have a very complicated boundary, you need a lot of measurements, especially if you have a very short length scale, because then sort of things are more wiggly and they want to sort of escape your measurements. So then you need to have a lot of measurements, and of course, like the normal issues with cubic computational complexity, you encounter them quite quickly. But then, of course, then you also need to choose how many measurements you put on the boundary and things like this. So it's sort of a bit tricky. And then actually you typically end up with a lot of sort of numerical instabilities if you have like zero noise on the boundary, but then you have noise inside the model. So then actually sort of that's quite unstable. So you need to do all sorts of tricks to keep the inversion stable. Okay, so regression, but then, for example, in classification, so what could a boundary mean there? So, for example, this is the banana classification data set, which is, unfortunately, I think it's an artificial data set. For a long time, I thought it had something to do with bananas, but actually, it's just like the banana shape in the data, which probably gives the name. That was a bit disappointing, I had to say. But yeah, so boundary conditions in classification might, for example, if you know that in your input space there are regions or boundaries for which you are absolutely uncertain about the class. So for example here, the outermost black line is the decision boundary which is sort of preset. So we know in this case, for some reason, that along this boundary in the input space, there's no chance we know anything about the class. And we want to encode that as in the prior we put into the model. So here you see how the decision boundaries then evolve with just four basis functions, 8, 16, 32, and 64 basis functions. After this, it really doesn't change anymore. So this is the model thinks this is a good idea. And yeah, it works. It works great. Then like a real data set, because the banana thing was not real. We scraped some data from a web page where you can report tick observations. You know, these really annoying small animals. Everyone knows ticks are. Yeah, I think this is sort of a global thing. Everyone hates them. So we have some 4,500 data points in the Netherlands, and we want to model the tick density. Like we have like a density function which we want to find. So it's basically a log Gaussian Cox process model, which is like a Poisson likelihood. And of course, like you can set this up. It's a standard GP task, like modeling like the log intensity function as a GP. And then the domain is actually it's just the map of the Netherlands, because there are a lot of rivers and lakes and islands. So then the ticks, they luckily don't swim that well. Of course, they swim if they attach to an animal, and the animal swims across. But then we constrained the model by the map of the Netherlands. And for example, here, this boundary is extremely complicated, and the discrimination is actually quite dense. So I think solving this sort of the eigenfunctions for this took like a couple of minutes, which is a long time. I'm quite impatient with these things. So that's a long time for me to wait. But so like a couple of minutes on my laptop for a problem like this, if that answers your earlier question, the computational load. So yeah, so then we get an intensity map. This kind, there's the small dots which are not showing very well, but are the observations, and then they are sort of clustered around certain areas. Okay, I'm slowly running out of time, so as a bit of a different kind of application. So the reason why I started looking at the boundaries was actually because of some work I did with Manon like 1.5 years ago. We wanted to do SLAM. SLAM is simultaneous localization and mapping, and a very sort of particular kind of SLAM. So basically, the smartphones you have, they have a compass sensor, and that compass sensor is a magnetometer, and that magnetometer can observe, of course, like what the compass does, it observes the Earth magnetic field directions. But you might not know that the local magnetic field, for example, in this building, is disturbed by all the metal in the pipes and electrical cabling and so on. So actually there's like a unique fingerprint, for example, even in this space for the magnetic field. So if you can observe that local magnetic field with your smartphone magnetometer, which samples that at like 100 Hertz or so, and build a map of those anomalies in the magnetic field, you can then use that as a map for also like localization. And of course, like the magnetic field is governed by principles from physics, and those sort of Maxwell equations can be put into a GP prior, because like the magnetic field anomalies are actually quite smooth. So then this is a very nice way of setting up a quite practical GP model. I have a paper on this, so if you're interested in the more of like magnetic field stuff, you can check my website. But the idea here was to use that GP prior for the magnetic field to actually build a map of the magnetic field anomalies and also correct the drift in our sort of PDR path estimation of how we move. So then, of course, you end up with having a lot of troubles with computational complexity and so on. So basically, what we ended up doing, we set up a sequential Monte Carlo approach, a particle filter, where each particle in the filter holds its own GP map representation of the magnetic field in 3D. And that sounds quite heavy. And it would be if you wouldn't do something to approximate this, to set up an approximation for the magnetic field GP. And what we did is that we did like hexagonal tiling. The hexagonal tiles are like 5 meters in diameter, and I don't quite remember, might have been like 3 meters in height. And then the space is sort of decomposed in these tiles, and then once you go and the map grows, there's just more of these tiles added to the space. And of course, you want the GP to be sort of continuous between the tiles, so then we constrain the tiles to have sort of shear values on the boundaries. Okay, long explanation. Don't worry, I have a video of this. So this is actually me walking around with my smartphone in like a student computer space in Cambridge. And let's see. So here you see that these are the particles, and just like the map of sort of the particle with the highest weight is actually shown here. So you see it drifts. Now it's a bit uncertain where it should go, but when it sort of goes back, it realizes that what the map looked like on the previous round, and it starts using the map for actually correcting the drift in the path. And well, I can tell you this is a bit boring, this example, because now it sort of keeps building the map and improving the map, and it works. So it's. And of course, now the GP is actually quite interesting, because the magnetic field is a vector field. So the GP outputs are actually sort of 3-dimensional. So it's like a multi-output GP. So you really have a GP prior in the vector field governed by the Maxwell's equations. I think this is a very fun project. And it worked really well. And they even gave us the best paper award at the International Conference on Information Fusion for this. So this was a very, very nice project, all in all. And you see sort of it doesn't drift because it has built the map, and the magnetic field is informative. There's a lot of metal in the space, pipes in the floor, and so on. So it really, really works. And as I said, the map is 3D. So this really has like a 3D representation of in this case, it's just the magnitude of the magnetic field which is shown. Yeah. So this was sort of one of the motivating things to look at sort of constraining the boundaries. So just to recap, I've gone through like the reduced rank approach for approximating GP priors, and then using that for constraining GPs to arbitrary shaped domains with boundary conditions. And how that worked was utilizing the link between the Laplace operator and the sort of covariance, stationary covariance functions, which sort of gave sort of nice tools to actually sort of make this in a very scalable way. And of course, like this can be applied to various problems, but typically in like low-dimensional inputs, like spatial problems, like 2D, 3D, maybe 4D, I should work fine. I mentioned that it was sort of built on some papers. The constraining to boundary conditions is covered in the AS paper from this year. The original approach for like the link between the Laplace operator and the covariance functions, that's published just some weeks ago, and then also builds on the magnetic field SLAM things, which was published last year, and then earlier work on like variational Fourier features by me and Nicholas and James. More videos, codes, things are available on my webpage. I'm going to hang around for the rest of the day. If you're interested in chatting, please come and talk with me. Thank you very much. I think we have time for a couple of questions.
So, do you have any questions?
So in this SLAM project, the only purpose of these constrained Gaussian processes were for only speed up. Yes.
Yeah, basically yes. And of course, the Gaussian process was constrained also by the Maxwell's equations. So, so that was sort of. But I'm not going there here. But so it was sort of.
Another thing that you can do is to put like calculations into your driver, but you didn't understand. You didn't explain how to.
I didn't explain that. It's sort of a different story. Yeah. Yeah.
So the example that you gave of Netherlands,
Yeah.
it only has like 4,000 something points, yeah?
Yeah.
So it's like not really big data.
No.
It's more about the fact that you were using a non-Gaussian.
Yeah, non-Gaussian, and then having the complicated boundaries, like with the rivers and the lakes and the islands and things. Yeah.
So how is the scaling of the finite element method when you have higher dimensional inputs?
It's horrible. It's exponential in the dimensions, basically. Yeah.
And do you have any ideas of, like, in that setting, what other thing you could do to solve that? Or?
Then probably you wouldn't be using a finite element method. You would somehow otherwise sort of approximate the basis functions, probably. Like, I haven't really looked into that. Yeah, I think then finite element method probably wouldn't scale.
I read a paper the other day about calculating the Laplacian eigenfunctions, but with more natural boundary conditions, so that they were able to solve the problem, but such that they didn't get any spurious boundary condition effects.
Okay.
So they didn't have to then, it wasn't for the same sort of problem, but just by tweaking what boundary conditions you're using, there'll be boundary conditions in higher order derivatives,
Yeah.
such that you effectively don't notice
Yeah.
the bound, because you might not want boundary conditions perhaps.
Indeed.
So that's an alternative.
Yeah.
If you have a finite domain, but you don't want it far from the data, but you don't want it affecting your fit, that you can just plug that in instead.
Indeed, they are like sort of like absorbing boundary conditions, which sort of kind of tricks the model to think that the functions just sort of continue outside the domain.
And so
Yeah.
you just won't notice
Yeah, indeed. Yeah.
the effects.
Yeah.
It's quite flexible.
Any more questions? Okay, so let's thank Arno again. So the coffee has arrived, so we have 30 minutes before we start with the next topic.
Oh.